Hello, everyone. Today, I'm really happy to talk about fair assortment planning, which is my joint work with my advisor, Nakin from MIT, as well as Susan and Adi Vascaro. So before I start, I want to first talk about a motivating example in online marketplaces. So nowadays, many online platforms such as Amazon are trying to use some kind of algorithm to help with their assortment planning decisions. And one thing these algorithms would do is they would try to prioritize those items with either the highest popularity or revenue. So if you search for a coffee machine, for example, on Amazon, one thing you would see is this coffee machine right here featured as Amazon's choice. And this right coffee machine, you're only able to find it on page 2 in the middle of that page. But if you look more closely, these two coffee machines are actually pretty similar to each other in terms of their ratings as well as their prices. But this coffee machine right here is certainly getting a lot more purchases because it's receiving a much higher user exposure, while this coffee machine is receiving a low and somewhat unfair amount of user exposure. So there are many problems associated with the kind of algorithmic decisions that Amazon is using. One thing is the reduced customer exposure for coffee machines like this. And in the long run, this kind of decision is also going to hurt the platform because it's going to introduce this kind of getting richer phenomenon in the sense that only the products that are keep being seen by the customer can get more and more popular. So I want to also emphasize that this kind of phenomenon can be seen everywhere, for example, on job recommendation sites such as LinkedIn, and also on social networks such as Instagram. And this motivated us to ask the following question, which is, can we design some kind of fair assortment planning algorithm that help us treat items on online platforms in a fair manner? And here, when we say fair, what we mean is we want any two similar items to get similar amount of visibility or customer exposure. Now, let me formally define what I mean right here by first introducing our model. So we consider some online platform with n items, each indexed by I. Each item has some popularity weight Wi, and the sale of this item is going to be generating revenue Ri. Now, if the customer gets offered assortment S, they will choose item I in S with this amount of probability, which is essentially the multinomial logic model. Now, the platform's goal is they wanted to try to select some assortment S that contains at most K items, which maximizes either the market share or the expected revenue, depending on what platform it is. Now, in this talk, I'm going to primarily focus on expected revenue because market share is really just a special case of the expected revenue function. And as I've mentioned, the platform also wanted to ensure fairness for all of its items. And I'm going to formally define it using this pairwise notion of fairness. Now let PS be the probability that platform offers set S. We define the visibility VI of item I to be the sum of all of the PS for all of the I's in S, which is essentially the probability that item I gets shown to the customer. We also consider this function Qi, which can depend on either Wi or Ri, to be some arbitrary measure of quality or merit of item I, which is known to us. And here, when we say we want it to be fair, what we mean is we want each item to have the same visibility to quality ratio, meaning that this kind of relationship should hold for every pair of items. And we also realized that this might be too strict to implement in practice, so we relaxed this condition a little bit by additionally introducing this delta, the fairness parameter. So basically, if you increase delta, you are being less fair in the system. Now, having seen all of that, we have arrived at the platform's optimization problem, which is a linear program with exponentially many variables. Here, we wanted to maximize the expected revenue as our objective, subject to the fairness constraints as well as the probability distribution constraint. Now, I want to mention that without fairness constraint, there always exists some single optimal assortment that the platform can just keep showing to its customers. But now with the fairness constraints in mind, we need to do some kind of randomization. But the difficulty right here is that there are exponentially many sets we need to consider. Luckily, we also showed that there always exists some optimal solution to this problem that randomizes over a polynomial number of sets, and this is the kind of solution that we are hoping to find. Now, before talking about how we solve this problem, let me first summarize our contributions in this work. So we have already showed the fair assortment planning problem using our novel pairwise fairness notion. I'm going to then introduce a fair ellipsoid-based framework that gives us near optimal algorithms for this problem, which depend on both the ellipsoid algorithm as well as a beta approximate separation oracle for its dual problem. To design the separation oracle right here, we will show its equivalence to an infinite series of knapsack problems. And in our work, we have designed a half approximate algorithm and a p-test for maximizing the expected revenue setting. In the special case, when we are maximizing market share, we are able to do something that's even better and design some FP tests for the problem. Finally, we also conducted some case study on a movie lens dataset, just showing the efficacy of our approximation algorithms in the real world settings. All right, so going back to our platform's optimization problem, the first thought that came to us when we see this difficulty right here is perhaps we can just look at the dual problem and transform things into exponentially many constraints. And that's exactly what we are about to do. Here is the dual problem that we are concerned about, where the zij's are simply the dual variables associated with the fairness constraints. And this row right here is the dual variable according to the probability distribution constraint. And here we have exponentially many constraints that we need to consider that we call the dual fairness constraints. And while this might look very complicated at first sight, this entire term right here, we can essentially just think of it as the fairness cost of item I. And this entire term, just think about it as the cost-adjusted revenue term associated with set S. So this constraints right here really just come to the maximization problem of this cost-adjusted revenue function right here. So if we can solve this maximization problem, then we can solve the dual problem as well as the original problem, then problem solved for everything, right? But unfortunately, what we see that maximization of problem of this cost-adjusted revenue function is actually an NP-complete problem. So there's really no easy solution for that. And we need to change our plan a little bit now to maybe design some kind of beta approximate polynomial time algorithm for that instead. And suppose we have that, this essentially would just serve as some beta approximate separation oracle that we could use along with the ellipsoid method. And together, these will give us some beta approximate solution to this original optimization problem. And what's even nicer is that this solution is going to come with the randomization over a polynomial number of sets. So this is really the property that we are looking for in the first place. Now, everything boils down to just designing some beta approximate separation oracle right here. And we're going to do that by introducing the equivalence of this maximization problem to an infinite series of knapsack problems. And in particular, the kind of knapsack problem we consider will take a special form that looks like this, where the utility of each item is going to depend on the capacity level W. And we show this very interesting theorem that says the maximization problem that we care about is basically equivalent to the maximization of those knapsack problems for all of the W greater than equal to 0. But solving these is also challenging because on one hand, there are infinite number of them. On the other hand, when this capacity level W increases, the utility decreases. So we don't really know for which of these W we are attaining the maximum. And that's the challenge that we are going to be tackled in the design of our approximation algorithms. So due to time constraints, I'm not going to go into the detail about our algorithm, but I will mention that we first designed this half approximate algorithm for those knapsack problems, which rely on a very interesting idea that we call adaptive partitioning. And then with the help of this half approximate algorithm, we then designed a p-test, which is able to achieve arbitrary accuracy. So together, they gave us access to a half approximate algorithm as well as a p-test for the original problem right here. All right, so now I'm going to end this talk with a very brief mentioning of our case study on a movie lens dataset, where we essentially apply our approximation algorithms to a movie recommendation problem. And the main takeaway that we are able to get from here is that we see that fairness can actually be imposed at a very little cost to the platform. So what we observed in this case study is that when the platform, even if it's being super fair to the movies according to their ratings, the loss in market share it's experiencing is not that big, and the platform doesn't even to randomize over a large number of sets to achieve a high level of fairness. So that is why we really hope that via our work, we can motivate a number of online platforms to take fairness into account when they are making their assortment planning decisions. And that concludes my talk. Thank you very much. And if you want to look at more details, here is a link to our paper.